Hi, everybody. Welcome back, physics fans. We're going to be talking about capacitors today. This video is a lesson about some of the finer details, I guess you might say, of capacitors and combinations of capacitors. We're also going to talk about the most basic design of capacitors, which is the parallel plate capacitor, and what determines the amount of capacitance that a capacitor has. So I'm also working under the assumption that you've already learned a little bit about capacitors and you have the basic definition. Here's our objective. We're going to be working on some parts of this, especially the time constant is what we're going to start with, and then also combinations of capacitors. So here's an interesting idea about capacitors. So if I charge a capacitor or discharge a capacitor, it takes time to build up the charge. It takes time for a capacitor to lose its charge. And the amount of time depends on resistance and capacitance. And we have this quantity of time, which is usually denoted with the Greek symbol tau. It looks like a T, but that's the Greek letter tau. And tau is known as the time constant. If you multiply resistance times capacitance, that is equal to an amount of time. It's interesting that the units work out like that. If you take the units of resistance, ohms, and multiply by the units of capacitance, farads, it gives you a number of seconds. So this is an amount of time measured in seconds. It's called the time constant. I have some examples, and we're going to look at why this matters. Why should that be the case? Why should there be this thing called the time constant? So let's go ahead and look at this example I have ready to go. And also this idea basically is that hopefully this makes sense that, hey, this is telling us that the greater the resistance or the greater the amount of capacitance, it's going to take a greater amount of time. The time constant would be a greater value. And we're going to see that illustrated in some of the examples that I have. So I have a little animation here and a bar chart. So there's actually a lot going on in this little animation. You might want to rewind the video or back up in the video and watch it again if you need to. But what we're going to do is flip the switch and see the capacitor charge, and then we're also going to flip the switch and see, flip the switch the other way and see the capacitor discharge. For this particular circuit, and here I've just got some representative values. Suppose we had a 6-volt battery and a 5-ohm resistor and a 0.1 farad capacitor. The time constant would be the product of the resistance 5 ohms and the capacitance 0.1 farads. 5 times 0.1 would give me 0.5 seconds. Yeah, seconds is interesting. Ohms is volts per ampere. And then I'm multiplying by farad, which is coulombs per volt. So the volts cancel, and then I get coulombs divided by amperes. And what do you know? That is a number of seconds if I multiply those two quantities. For this particular circuit, when I first start charging the capacitor, the initial current will be 6 divided by 5, 6 volts divided by 5 ohms would be 1.2 amperes. And then eventually the charge that will be stored is going to be 0.6 coulombs, which is 6 volts times 0.1 farads. So watch the animation. Here we go. We're going to charge the capacitor by flipping the switch to the down position. And it happens pretty quickly in our first example here, but there would be initially a current that's going to start dying immediately. So there's this current that starts going into the capacitor, but the capacitor starts to build up charge, and it takes some time for that to happen. 0.5 seconds is not the time for it to happen. It would take about 6 times that amount of time for it to completely charge. So roughly six time constants, or in this case, 6 times 0.5 would be 3 seconds is the amount of time to completely charge the capacitor, more or less completely charge it. That actually would get you up to about 99.9% of its final charge in 6 time constants. Let's flip the switch the other way, and the time constant is the same for discharging. So it's going to take about the same amount of time to discharge the capacitor through the same resistance. So we're going to flip the switch up and then watch what happens. It takes about the same amount of time, actually precisely the same amount of time to discharge the capacitor as it would take to charge it with these values in this circuit. Now, let's play around with our circuit. We're going to start doubling some things. So it's interesting that the time constant depends on R and C, but not the voltage. So let's look at our next slide here. What if I doubled my voltage? So now I have twice as strong a battery, say it's like 12 volts instead of 6 volts. Well, that's going to cause two things to be different. That's going to cause my current to be greater by a factor of 2, my initial current, because now I have more voltage, same resistance, but I doubled the voltage. I have doubled the current. But I also am going to end up with twice as much charge stored in my capacitor. And for that reason, I doubled both things. It's going to take the same amount of time. I'm sending current in more rapidly, but I'm sending charge into the capacitor more rapidly because there's a higher current, but it also holds more charge or gets to a greater charge because I'm applying a greater voltage. So let's just watch this happen. My current's going to be more, my charge is going to be more, but the amount of time is going to be the same. So that was the charging. Let's watch the discharging. Again, it'll take the same amount of time to charge or discharge. Depends on RC. It's not equal to RC, but it's related to RC. R times C is the time constant. Let's look at another example. What if we now double our resistance? Well, now, if I double resistance, but everything else stays the same, I hope it would make sense to you that that's going to decrease the current by a factor of 2. Twice as much resistance, half as much current. And that's going to slow down my charging rate. I'm going to put the same amount of charge into my capacitor eventually. That's going to be 1.2 coulombs in this case. But now I'm sending it in at a lower rate. 1.2 amperes is the rate at which charge is flowing, at least initially. Now, all of that changes as the capacitor charges, but hopefully intuitively it will make sense to you. Okay, well, we doubled the resistance, so I'm charging at half the rate. It's going to take twice as much time. So notice now my time constant is 10 times 0.1, and that's 1 second. That's twice the time constant we had in the previous circuit. So let's watch this charging occur. And that transition took about 6 seconds, which is accurate. If you had a circuit like this, it would take about 6 seconds to charge the capacitor, about 6 times the time constant. And that's going to get you pretty much completely done with the charging process. Now, if I flip the switch up, it's going to take about the same amount of time, or precisely the same amount of time to discharge. So I hope that you can see why resistance would affect the time constant. It affects the time to charge or discharge the capacitor. Let's try another change. Now let's double one more thing. We're going to double the capacitance. And now I'm putting more charge into my capacitor because it can hold more. Remember, capacitance is a measure of the ratio of charge to voltage. So with the same voltage, if it's more capacitance, then it will hold more charge. So initially, my current's going to be the same, but it's going to take more time now because I'm putting more charge total into the capacitor. So if we watch our animation again, now we will have doubled the time again. My time constant is now 10 ohms times 0.2 farads is 2 seconds. And that means it's going to take about 12 seconds for this overall process to occur. So that's going to take a while. Let's go ahead and get started. So flip the switch down, And then I have the same amount of current initially, but now my charge is a greater amount. So it's going to take more time to fill up my capacitor because it holds more per volt. It's got 0.2 farads, 0.2 coulombs per volt. I hope that helps you understand why the time constant would depend on C, the capacitance. If it holds more, it's going to take more time to fill it up, so to speak. And likewise, it takes more time to release the energy that's in it and the charge that has been stored. So I hope that these animations and this explanation helps you understand the concept of the time constant. A little detail about the time constant. Time constant is a little bit like the concept you might have heard of before, half-life. If you have a radioactive material, it takes, say, 3 days for it to undergo half, to decay to half the amount. Every 3 days, it drops by half. Well, the time constant is a little bit like that, but it is actually not half, but rather 37%, which is kind of a strange amount. But when we're discharging a capacitor, every time constant that goes by is 37% as much charge remaining as there was to start with. So 37% of the original, and then 37% of 37% after another time constant, and then 37% of 37% of 37% after 3 time constants, and so on. After 6 time constants, you've got 37% raised to the 6th power, and then you're down to like less than about a 0.2% remaining charge if we were discharging. But the key thing here is just to realize that this is giving us a sense of how much time it's going to take to charge or discharge. Now, moving on, we're going to talk about combinations of capacitors. And if you look at these formulas, they should look familiar to you. Hey, I've studied circuits. I know something about resistors. And, I've got these formulas for resistors. You might say, oh, yeah, I already know this. I know series and parallel. But wait a minute. Did you notice that they're backwards? The formula that has me adding capacitance values is for parallel capacitors. The formula that has the reciprocals in it is for series capacitors. If you had the same formulas for resistors, it works the other way around. If you have series resistors, you add up the values. If you have parallel resistors, you add up the reciprocals of the resistance values. So why do we have these formulas for capacitors? Let's look at that, and I have some examples again, some numerical examples to help you understand that. So let's suppose that we have these two capacitors, 0.1 farad and 0.2 farads. And we connected them like this. I hope that you can recognize, oh, those are connected in parallel. So the rule for parallel capacitors is to simply add the amounts. C1 plus C2 would give me the equivalent capacitance of the two capacitors combined. So that's going to give me 0.3, simple math, 0.3 farads. And what that's telling me is the equivalence of these two combined. If you had them in a box and you put them in a circuit, you would not be able to tell the difference between the capacitance of that box, so to speak, and a 0.3 farad capacitor, a single capacitor equal to 0.3 farads. So that's the idea of an equivalent capacitance, or effective capacitance it might be called. Let's put it into an imaginary circuit and think about how that makes sense. So let's suppose that we hooked up our pair of capacitors to a 12-volt battery, and then we charged them. So let's think about this. Let's just watch our animation here. There would be current, and in any current where I've got a parallel circuit, it splits into two parts. So some of the current would go to C1, some of the current would go to C2 while they are charging. But all of these things are going to end up at 12 volts. So once the charging is done, there's no current, and the voltage of my capacitors will each equal the same because they're parallel, and they're each parallel to the battery. And then we can use that to find the amount of charge that ends up in each capacitor. Charge will be given by C times V. So here at the bottom, I've shown how much charge would there be in each of these capacitors. Capacitor 1 would have 1.2 coulombs. Capacitor 2 would end up with twice as much. It's the same voltage if it's parallel, but it's twice the capacitance, so it holds twice as much charge. Let's label those amounts in our figure and think about what's going on. Well, okay, how much charge came out of the battery and ended up in those two plates? Well, the total amount of charge is 3.6 coulombs. And if we think about this unit, say, imagine the whole thing is in a box, and you ask yourself, well, how much charge went into this box? The answer would be 3.6 coulombs. This box was connected to 12 volts. Capacitance is charge per voltage, and 3.6 coulombs divided by 12 volts is 0.3 farads. And that is the same thing as the equivalent capacitance, the effective capacitance. So that's how that makes sense to say, oh, these two guys together are like 0.3 farads. They're equivalent to 0.3 farads. I think that's pretty easy to understand. I hope that makes sense to you. Anytime you add parallel capacitors, you're basically just increasing the amount of charge you can store because you end up with the same voltage. They all have the same voltage, so I just get more and more charge. No matter how many I keep adding in, I'm just going to keep upping my capacitance, so it's simply the sum. Series capacitors, I think, are trickier to understand. So let's look at this. Here are two capacitors, 0.4 farads, in series with 1.2 farads. So this is where I would use the reciprocal formula. 1 over C1 plus 1 over C2 is equal to 1 over C equivalent or effective. And check out what happens here. Now I chose these numbers on purpose, and that ends up being 0.3 farads. Same as our parallel capacitors in the previous example, except now look at the capacitance values. That's interesting. Both of these individually are greater than 0.3. And if I put them together, I actually end up getting less than either one of them. The same thing happens with resistors. If you put resistors in parallel, that same formula, for parallel resistors, you end up with less resistance if they're in parallel. With capacitance, it works the other way around. You end up with less capacitance if you put them in series. So why does that happen? And how does that make sense? This is a little trickier. So we're going to do something a little bit different here. But again, let's imagine putting this into a circuit and charging. And I want you to watch carefully here. This is a series circuit. There's only one current. There is no place where current's going to split up. So watch the current arrows that I'm animating here and think about how current's going to flow. If they're in series, they're both charging at the same time. They're both getting the same current. The rate at which charge is building up on one is equal to the rate at which the charge is building up on the other. You might even be a little bit puzzled if you look at this circuit, like, why is there any current in this part of the circuit? Well, if charge builds up on this plate and it becomes positive, that's going to attract electrons to this plate. And where are they coming from? This plate. So it ends up causing an equal amount of current in this wire in between the two capacitors. So if they're connected in series, they have to have the same current, and that's an important part of this type of connection. Important part of understanding this type of connection. But now let's think about the math. And now we're going to kind of go backwards. So according to our formula, this is supposed to be equivalent to 0.3 farads. If I put them in a box and I didn't know what was in there, well, it's supposed to be a 0.3 farad box. And if I use my formula, Q equals C times V, and I've connected it to 12 volts, I'm kind of expecting, hey, well, if that's a true formula, 3.6 coulombs should go into that box. So I'm taking a different approach to this analysis. So let's just suppose that our equivalent capacitance formula is true, which it is. Then 3.6 coulombs would have to go in. How does that make sense? Well, now let's think about what's happening. I'm going to move that number over here. Now let's think about what's happening to each of our capacitors. Well, capacitor 1 is getting that much charge, and that means its voltage would be 9 volts. So we're doing something different here. Solve for the voltage of capacitor 1. It's not 12 volts. It's not connected to the 12 volts directly. And if it gets 3.6 coulombs, its voltage would be 9 volts. If we look at the next capacitor, it gets the same amount for reasons that we explained. As the charge is building up on capacitor number 1, simultaneously it's building up on capacitor number 2. The current is the same at all times. So if the rate is the same, the time is the same, the charge is the same, conservation of charge. There has to be this much charge transferred in between the capacitors, which means capacitor 2 also gets that much charge, and its voltage is less. This might seem weird that, okay, capacitor 1 is a lesser capacitance, but it has a greater voltage than capacitor 2. Well, that's just the way the ratios work. A capacitor has a constant ratio of charge to voltage. So if it's got the same amount of charge, but a greater capacitance, it's going to be a lower voltage. Now, I hope that being a student of circuits, you have noticed something about these two numbers. The two voltages, they add up to what? 12. And that should make perfect sense to you. That, yeah, everything in this circuit makes sense if you think about it. Like, okay, those two numbers have to add up to 12. If I'm using a 12-volt battery, that's like a loop rule. Once they're charged, still going around the loop, the voltages have to add up to 0. So up 12 at the battery, and then down 12 going through both capacitors, down 9 and then down 3. That would be consistent with Kirchhoff's loop rule, which it has to be. And each capacitor is illustrating what it should illustrate, our basic capacitance concept. Capacitance is the ratio of charge to voltage. And the whole thing is illustrating that, okay, when I hook this package of capacitors up to this battery, I got 3.6 coulombs going in, and that was using 12 volts, and that makes it equivalent to 0.3 farads. So I hope that this illustration would help you understand series capacitors. Add any number of series capacitors together with the same concept. You would always end up with less and less and less and less capacitance the more you add. You're not helping your capacitance by putting them in series. You're actually decreasing the overall amount of capacitance. And I guess the simplest explanation would be that, well, you're splitting up the voltage that you've got to work with among all of these capacitors. And that's going to have the overall effect of less charge stored for a given total voltage. Okay, now the last part of our video is going to be an overview of the most basic and simplest design of capacitors, something called a parallel plate capacitor. And this is our objective here. What is this relationship? And how do we use this relationship to understand capacitance? A parallel plate capacitor is a pretty simple idea. You have two metal plates or conducting plates separated by some sort of material in between, an insulator. And that's pretty much all there is to it. And the formula for this, capacitance, which we know should be the ratio of charge to voltage, but it has a connection to the properties of the design. Like, okay, what is this capacitor made out of? A couple of plates. How big are they? Well, each plate has a certain area measured in units like square meters. And how far apart are these plates? Well, they're separated by a certain distance, d. And what have I put in between them? There's a constant called the dielectric constant, which is a measure of the material a property of the material that's in between the plates. Well, all of those things and the permittivity constant, epsilon naught, which is the same permittivity constant we've seen before in electrostatics, is also involved in this formula, a constant that goes in there. All of those things together give us what's called the capacitance, or it's equivalent to the capacitance of this design, this particular kind of design. Here's a diagram that you could add to go with that. And in the upper left-hand corner is kind of your usual way to visualize it, very similar to the schematic symbol for the capacitor, which is just two flat plates separated by some gap. And the gap could be filled with a material, could also just be empty, full of air, or even a vacuum. We just need some sort of insulator in between the two plates. We want charge to build up on the plates, but we don't want charge to go from one plate to the other. So we have to have this gap, and we have to have this filler, whether it's literally something or even the lack of something, a vacuum. The dielectric constant or dielectric slab, kappa, is the symbol we use for this constant. And the simplest thing to say about that is that, okay, the constant kappa is like a multiplying factor. It doesn't have any units. It's a ratio of how good is the capacitor with the material versus what it would be without the material. Kappa, by definition, is 1 for a vacuum. So that's kind of the basis for kappa. We're comparing how good is this capacitor with the material, like, say, Pyrex, compared to what it would be without the material, a vacuum. If you have Pyrex between the plates, it's 5 times better. It's a better capacitor. It holds 5 times as much charge for a given voltage than if it has vacuum between the plates. Nothing, literally nothing. Notice that air between the plates is really close to the same as vacuum. So for all practical purposes, we usually just treat air and vacuum as having a constant kappa equal to 1. In our chart here, these are just some example values. It's not the sort of thing you would memorize. It's something that you could look up if you needed to, or you would typically be given in a problem. And notice these various materials can be used to separate our plates. We have the clear winner strontium titanate, which is a specialized material which has a very high dielectric constant. And there you can look up all kinds of numbers for this sort of thing. But just know that there's a certain value associated with what material separates our surfaces. Now let's look at an example, plugging some numbers into this. You can make a capacitor using really simple things. So if you had a book, you can make a capacitor using the pages of a book and a couple of pieces of aluminum foil. Just slide them in between the pages and then close the book, and that would be a capacitor. I have some numbers based on an actual experiment that can be done, which I've done on many occasions, where we put aluminum foil between the pages of a particular book. In this particular book, 250 pages is a thickness of 2.13 centimeters. And then each piece of foil is maybe 21 centimeters by 16 centimeters. Notice the dielectric of paper was from that previous table, about 3.7. And then if we wanted to, we could calculate the capacitance. So let's do that. If we made our own capacitor, how good would it be? How many farads would it be? Let's find the capacitance using our formula. So I've got everything shown here, and take a few minutes and look over this. If we have the thickness of 250 pages, we can find the thickness of one piece of paper. So that would actually be the distance separating our two pieces of aluminum foil. And that's shown here, where I'm dividing the thickness of 250 pages by how many there are. This would be the thickness of a single piece of paper, and that's going to be the D in our formula. It's the thickness of this material that's separating our two surfaces. And that's sometimes called the dielectric slab. That's a great name, slab. It's just a material that's filling the space between those two conductors, which in this case could just be a couple of pieces of aluminum foil. And then our formula shows kappa times epsilon times A. Well, kappa depends on the material. So this is paper, and we could look that up. Paper kappa is 3.7. Epsilon naught is a value that you can find. It's a physics constant. It's 8.85, 10 to the negative 12 coulombs squared per Newton meter squared. And then I'm multiplying by the area. Now the area of a rectangular piece of aluminum foil would simply be width times length. So 0.21 meters times 0.16 would be the area in square meters. And then I'm dividing by the thickness. So there are the numbers in this formula, and that would give us a result, 1.3 10 to the negative 8 farads, or 13 nanofarads. How do I get farads? Farads is supposed to be coulombs per volt. Well, the meter squared in the area and the meters separation would cancel, leaving just meters, and then our constant, the permittivity constant, is coulombs squared per Newton meter squared. And so that's going to give us a result here that is going to be equivalent to coulombs per volt. It may not be super obvious if that's the case, but I end up with coulombs squared, and then on the denominator I've got newtons times meters squared. That's joules meters. So that's newtons, Newton times meter, and then one of my meters cancels. I end up with joules, and then I've got coulombs per joule, which is 1 over volts, and then I also have coulombs. Write it out, and you can figure it out. This is going to be equivalent to farads. Notice that's not a lot of farads. Like, that's a really pathetic capacitor. Yeah, it was easy to make, just get a couple of pieces of aluminum foil, but that's not a very good capacitor. It's a really low value. But a lot of commercial capacitors are measured in microfarads or millifarads. They also have kind of a class of capacitors known as supercapacitors that can be as great as 1 farad or even higher, 50 farads. So look at this formula and think about the logic of it. If we just think about the kind of formula, well, capacitance is proportional to area. I hope that makes sense here. We're storing charge on these surfaces. If I have a bigger surface, I can put more charge on it for a certain voltage. Remember, this is also equivalent to charge per volt, Q over V. But if I have a bigger area, it's basically just more space for my charge to spread out. Wow, that actually makes perfect sense to me. The 1 over D is maybe not as obvious, but if I put my plates really close together and I apply a voltage, then where these opposite charges are getting close together, they attract one another. So they end up cramming more in there tightly. So I end up with more charge per volt, or charge per voltage, if I have a lesser distance between my two surfaces, if I could squeeze them really close together. Think about this. If you wanted to get a 1 farad capacitor using the same approach that we were doing here, I need a much bigger piece of paper and much bigger pieces of aluminum foil. If it's proportional to area, I need 10 to the 8th times the area, which is 10 to the 4th squared. That means I need it to be about a piece of aluminum foil. 10 to the 4th is what? 10,000 times bigger on each side. So not 0.16 meters, but 10,000 times that, which would be what? I don't know, the number of kilometers. This would be like a piece of aluminum foil the size of a city to get to 1 farad. Or I need to change the distance. I need really thin pieces of paper somehow, like 10 to the 8th times thinner. And that's just not practical at all, because I would have a thickness less than the size of an atom. So to get to a farad is kind of an amazing feat, if you will. A farad is actually a large a relatively large capacitance. But it depends on those two things, and then some constants. So we have the one constant that doesn't change, and then, oh yeah, I could also maybe find a material that works better. So if you remember from the previous slide or two there, kappa for strontium titanate was 200 something. So that would also be a way to increase the capacitance depending on the material. Here's an interesting thing we can do with this formula that we're learning about, a formula for a parallel plate capacitor. We can solve for the electric field that's present within a capacitor. That's an interesting exercise. And I think that understanding this electric field helps you understand capacitors, and also can have some applications in other situations, like say Millikan oil drop experiment or the electron gun concept. We can get the field in between the plates based on the charge that exists on the plates. So how do we do that? Well, I've got it shown here, but here's something fun you might try. Derive it yourself. See if you can figure this out. Can you take the formulas that are given here and derive E, an expression for E that gives you how strong the field is depending on the charge that exists on the plates and the dimensions of the plates. What's the area of the plates and so on. You could pause the video and try it yourself. I'm getting ready to show you what it looks like. One thing we might do is take our new formula, which is how to find capacitance based on the dimensions of the capacitor, and set that equal to Q over V. In other words, equate the two formulas. That's a pretty obvious thing that we could do. But then we could rearrange that. There are different ways you might do this, but what I did here is I just kind of rearranged that proportionality. You can cross multiply and kind of rearrange a couple of things and show that V over D should be equal to Q over kappa epsilon naught times the area. But V over D, if you think back to something hopefully you learned in electrostatics, has a connection to E, the electric field. So I have that shown here. The electric field should be equivalent to delta V divided by delta R, the strength of the electric field, for a uniform field, which this should be. But hey, that's the same thing as the voltage of the capacitor divided by the distance between the surfaces. And that means the field in between should be given by this formula. Hey, did you pause the video and try it yourself? I hope you did. If you did you get that answer? If you did, way to go. So here's a formula we can use to find the field inside a capacitor. And you might find that in certain situations where you would need to use that idea. You could either try to remember this formula, which is kind of a hard one to remember maybe, or just notice that you can derive it based on other ones that hopefully you know. And if you're doing physics too, it would be on the equation sheet. So what do we make of this formula? Well, one thing to point out about it, a couple of more details about it, is that it's a formula that would give us the field inside the capacitor. And we're making some simplifying assumptions when we derive this. We're really assuming the field is perfectly uniform, but it's not perfectly uniform. It is quite uniform, especially if you're down inside the capacitor. So it's going to be most accurate for the region interior to the capacitor. But then once you get outside of the capacitor, everything is different. The field gets much weaker. Kind of starts to curve out or bulge out at the edges, kind of curves around the edges. This is sometimes called the edge effect. And outside, the field is essentially zero, especially in comparison to how intense it can be in between the plates. Typically, the plates are really close together if you have a capacitor. So anyway, keep in mind that the formula we're talking about here is only for the inside part of the capacitor. But then the other thing to point out about this formula is it helps us understand the behavior of a capacitor and also the significance of kappa. So what's up with kappa? If we had nothing in between the plates, then kappa would be 1, and the electric field would be Q over epsilon A. But when we insert a dielectric material, an insulator, what happens is that causes the overall net electric field to get less. It gets weaker. Notice we're dividing by kappa. So if kappa is, say, 2, the field would be half as strong with the material as it would be without the material, whatever that material might be. And some of them have a value close to 2. But if we just use that as a simple example, if you put the material in there, your field is weaker by a factor of 2 if you have a kappa equal to 2. Why does that happen? That happens because of the induction effect. So what happens in our insulator material is that there is an opposing field induced. It's going to separate charges within the inductor. There won't be a current through the conductor, or there will not be a current through the insulator, but there will be the induction effect that will cause kind of a rearranging of charge within the insulator. And that produces an opposing field, and that weakens the overall net field. Kind of a key concept there. We're talking about the net field whenever we use this formula. Because the field is weaker, that's going to allow, it's going to cause there to be this idea that, well, okay, I put a certain amount of charge on there, my field is not as strong, my voltage is not as great. That's going to lessen the ratio of charge to voltage. And that's why this has an effect on, that's going to actually increase the ratio of the charge to voltage. It's going to lessen the electric field. I didn't say that right. But that's why we have this factor in here. Basically, kappa causes the field to go down, but it causes the capacitance to go up. Because for a given voltage, I can pack more charge on my surfaces. That's why kappa has an effect on capacitance. I hope this video helps you understand some of the finer details of capacitors. Good luck working all those capacitor problems.